All right, so you've probably learned about gravity in class, right? That classic formula, PE equals mgh? It's super useful for things happening here on Earth's surface. But what about satellites or planets locked in their cosmic dance? Well, for that, mgh just won't cut it. Today, we're going to dive into the real physics of gravitational potential energy, the kind that works on a cosmic scale.
And to get our heads wrapped around this, let's start with a bit of a puzzle. Why is it that the gravitational potential energy of anything in orbit, say a satellite or even our moon, is always a negative number? Think about it. The mgh formula always gives a positive answer if something is height. So that old formula can't possibly explain this. It's a clue that we need a deeper, more fundamental way to look at gravity. So here's our game plan. We'll start by looking at why our surface-level gravity model has its limits. Then, we'll introduce a really key idea, the infinity reference point. This is the secret to building the universal formula, which we'll actually put together step by step. After that, we'll clear up some important terms, and then the fun part. We'll apply all this to the cosmos. Let's get started. Okay, first things first, we need to understand the limits of what we already know. That PE equals mgh formula is a fantastic tool, but it really only works under some very specific and limited conditions. See, the whole idea behind mgh rests on one big assumption, that the force of gravity, that little g, is constant. And you know what? Close to Earth's surface, that's a pretty safe bet. But what if you're launching a rocket? As you climb thousands, then millions of kilometers away, Earth's gravitational pull gets weaker and weaker. The value of g is constantly changing. And that's where mgh just completely breaks down, and we have to switch over to Newton's universal law. So to build a formula that works everywhere, we need a new starting line, a new 0 point. Here on Earth, it's easy. We can just say the ground has zero potential energy. But out in the vast emptiness of space, where is the ground? What do we set as our zero? Well, physicists came up with a really clever solution. They define the zero reference point as being at infinity. Now, don't get hung up on that word. It's not a real place, it's just a concept, a point so incredibly far away from a planet like Earth that its gravitational pull essentially drops to zero. This gives us a universal, consistent starting point for all our calculations, no matter where we are in the universe. And this is where things get a little weird, but it's so important. If we define zero potential energy as being infinitely far away, then the potential energy of any object closer than infinity has to be less than zero. It must be negative. And that is the answer to our puzzle from the beginning. Here's how to think about it. Picture an asteroid way out at infinity. It has zero potential energy. Now, as it starts to fall toward Earth, what's doing the work? The gravitational field is. It's pulling the asteroid in. Since the field is doing the work, the asteroid is losing potential energy relative to where it started. And if you start at zero and lose energy, you end up with a negative number. Okay, so we've got the concept down. We understand why the energy is negative. Now let's use that idea to actually build the formula. The challenge is calculating the work needed to move something away from Earth when the force of gravity keeps changing. We can't just do force times distance. We need to be a little more clever. The logic here is actually pretty simple. It's like, how do you eat an elephant? One bite at a time. We take the big problem of a changing force and break it into tons of tiny, manageable steps. In each tiny little step, the force of gravity is practically constant. So we calculate the work for one tiny step, then the next, and then we just add them all up. Finally, to find the absolute potential, we imagine that path goes all the way out to infinity. So for each one of those tiny steps, the math is just work equals the average force times the tiny distance. But that negative sign is so important. Remember, gravity is always pulling the object inward. We're calculating the work to move it outward, so our displacement is in the opposite direction of the force. That's where the negative sign comes from. Now, if we use calculus to add up the work done over all of those infinite little steps, we land on this expression. This tells us the total work needed to move a mass m from Earth's surface at radius r sub e out to some final point r sub n. Don't sweat the calculus derivation, just focus on the idea. We're summing up all the tiny bits of work. And now for the big payoff. To find the absolute potential energy of an object sitting on Earth's surface, we just set our final destination to be infinity. Well, what's 1 divided by infinity? It's basically 0. So that whole second part of the equation, the 1 over r sub n, it just vanishes. And we're left with this beautiful, simple, and incredibly powerful universal formula. U equals negative g times the mass of the Earth times the object's mass, all divided by the radius of the Earth. Okay, now that we have this awesome formula, we need to be really precise with our language. There are two terms that sound almost identical, but mean very different things. Gravitational potential energy, which we just found, and gravitational potential. Let's make sure we understand the difference. So, gravitational potential energy, which we call U, is the energy tied to a specific object, like a particular satellite. It depends on the satellite's mass. It's a property of the whole system, Earth and the satellite interacting. But gravitational potential, V, is different. It's the energy per kilogram. You can think of it like a map of the gravitational field itself. It tells you how strong the gravitational slope is at any given point in space, completely independent of whatever object you might put there. All right, enough theory. Let's put this stuff into practice. This is where we get to see just how powerful this universal formula really is when we start looking at actual cosmic scenarios. This table shows it perfectly. Look at how the gravitational potential, that property of the location, changes as you get further away. At 1,000 kilometers up, it's a significant negative number. But as you go out to 50,000 or 100,000 kilometers, that number gets smaller. It gets less negative, climbing closer and closer to that 0 point way out at infinity. Now, let's talk about some serious numbers. This right here, this is the absolute gravitational potential energy of our moon relative to the Earth. That is a staggeringly huge negative number. It represents the unbelievable amount of energy that binds the moon to our planet, the energy the field has spent to keep it in orbit for billions of years. So I'll leave you with this final thought. We've established that this negative potential energy represents being trapped in a gravity well. To escape, you have to add energy to get back up to zero. So what does this enormous negative number for the moon tell us? It's a measure of its bond to the Earth. It's the energy debt we would have to pay to send the moon flying off into space. It's a number that quantifies the deep, physical connection between our world and our constant companion in the night sky.